everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar, Headworks, the Start to Wastewater Treatment. My name is Zoe Eisel from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. Please note, GoToWebinar has recently gone through an update, and you can now add live captions or react using emojis. After the webinar, you will receive a follow-up email that includes a link to the recording and any other information you may need. You can also download the slides from today in the Materials tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. Our team is located across the country and can readily deploy staff or resources to meet your community where you are. Each of our partners brings unique experience and specialized expertise to address a wide range of community needs and expand the available services EFCN can offer. Through this network, EFCN works directly with communities and utilities to provide a wide variety of free, customized technical assistance services. Find only some of the ways our team can support your community listed here, and use the link in the chat to submit a request and receive tailored support based on your needs. Lastly, make sure to keep up with EFCN by scanning the QR codes provided or visiting the links I will be sharing shortly in the chat. Through these links, you can view upcoming webinars and trainings, sign up to begin receiving notifications for future events, and access the recordings of webinars you may have missed. And on that note, we can get started. I would like to introduce our presenter for today, James Markham, research engineer at the Southwest Environmental Finance Center. Welcome, James, and I will go ahead and hand it over to you.
Righty. 1 second here while I select the appropriate screen. All right, thank you everybody for joining us today in the first of our multi-part series on wastewater treatment on the wastewater treatment train. Today we're going to be talking about the Headworks. We're going to start with what it is and why it matters. We'll talk about some core components, some O&M considerations, how the Headworks impacts the entire plant, particularly if it's not well maintained. We'll talk about some strategic considerations for decision makers, and then we'll have our recap wrap up and Q&A. As Zoe said, I'm a research engineer at the Southwest Environmental Finance Center. We are in Albuquerque, New Mexico, close to the banks of the Rio Grande, and we do a lot of this kind of training and technical service. I've been with us for about 11 years now. As we get started, I'd like to take about 30 seconds to just get a quick poll of who's in the room. I think we had over 600 registrants, but this is always good to give us an idea of who we are talking to today. Zoe, if you wouldn't mind firing up the first poll really quick, we'll give it about 30 seconds just to determine, are we looking at mostly wastewater operators or trainees? Are you utility manager or director? I realize that particularly with small utilities, people wear a lot of hats. So if you sort of fall into more than one category, just pick the hat that you wear the most.
All right, it looks like most folks have voted. We
All
have
right.
7% as wastewater operator, trainee, or plant staff. We have 3% as utility manager, director, or board member, 58% as regulator or other government official, 21% as engineer, consultant, or TA provider, and 10% as other.
Okie dokie. Pretty knowledgeable crowd here. Thanks for joining us. Let's start off with a discussion of just what the Headworks is and really why it matters and what's going on here. And I do realize I'm preaching to the choir a little bit here, but we've got a lot of information to cover and a very short period of time to do it in. So when we think about wastewater treatment, most of the time, what we are thinking about is reducing influent concentrations to an effluent level that is acceptable for release back into the environment, making sure that we're not harming the environment, getting people sick, getting the environment sick. We've got a table here that's got a lot of the things that we're looking at, suspended solids, fecal coliform, nitrates, phosphorus, things like that with some typical concentrations and what we are trying to get to typically under either a state or federal discharge permit. What this largely ignores is all of the other stuff that ends up at your treatment plant as part of the influent stream that we have to get rid of in order to effectively treat our effluent. Basically, what I'm talking about here is trash. We're talking about, large, non-digestible inorganics like bone and sticks and roots, inorganic material like glass and sand and rocks, rags, building material, toys, pretty much anything that can end up in the sewer, including those non-flushable, flushable wipes that people insist on putting down the toilet. There is a lot of debris that can show up in influent, whether you have just a normal collection system, or even more so if you've got a combined system, like, for example, the city of San Francisco, where stormwater is also a factor. So dealing with this extra debris is really what the Headworks are all about. It's as important as any of the other stages. It really sets everything else up for success. And in many cases, the long-term efficiency of your later treatment stages really depends on the Headworks functioning correctly. This is going to be reviewed for most of you, but typical wastewater treatment train looks something like this. We start at the Headworks, where we're focusing on screening and grit removal and flow measurement. Might also have flow equalization and pre-aeration stages in there, depending on how the process is constructed. Then we move on to our primary treatment, which is mostly physical treatment, clarification and settling. Secondary treatment, biological steps, some sort of disinfection, either UV, or if it's chlorine, then we're going to add a dechlorination stage as well. And then eventually some sort of discharge, whether that's to a complete evaporation lagoon for some of the small systems we have out here, or for land application, or into one of the waters of the United States, in which case you're going to have an NPDES permit. Pretty much, we're going to spend our entire time in that green box today, but recognize that everything downstream working efficiently kind of depends on having a well-maintained Headworks and one that is operating efficiently. As I said, within the Headworks, we've got a number of physical processes that are going on, starting with screening, which is taking out sort of coarse materials with the larger bar racks and trash racks. We might have fine screening to take out smaller components. Then we've typically got a grit removal stage, which is focused on sand and gravel and similarly sized detritus. We might have, like I said, a pre-aeration stage or a flow equalization stage, which is essentially just a set of basins or holding tanks where we can keep excess flow from either peak events or from peak flow times during the day, and run it through the treatment plant without dealing with those sort of peaks and swells to even out our treatment processes. And last but not least, and really, really important, is the flow metering stage of this. I see this a lot in smaller systems that I work with, both in our state and others, where flow metering is something that they don't either pay attention to very well, or the equipment is not well maintained. And as we'll see, if you are not paying attention to flow metering equipment, it is very hard to prove that you are staying within your permit discharge and flow limits. and it makes it much, much harder to ensure that your processes are working the way they're supposed to. And you will notice there is some reiteration in this session, but really everything downstream really depends on working well on the headworks. For those of you who are operators or are some way involved in the wastewater treatment process, sort of not on a consulting or regulating base, of these four Headworks components that I've mentioned, which of these do you actually use? So if you can fire up the second poll question here. This is just a quick one. So screening, grit removal, pre-aeration, flow equalization, and flow metering. Which of those do you have in your current facility, or is this just not applicable to you because you're not actually running a facility?
All right, it looks like most folks have voted. 30% said screening, 22% said grit removal, 12% said pre-aeration/flow equalization, 22% said flow metering, and 68% said don't know or not applicable.
Okie doke. And that's about what I expected. As we'll see, pre-aeration and flow equalization are less common here in the United States, particularly with older plants. It's something that's used in Europe a lot to help keep a smaller footprint, and it's incorporated into more modern designs as well. So not unexpected that not everybody has all of those components, but they are good to be aware of, particularly if you're getting to that stage where you might have to be replacing some or all of your system. So why do we have Headworks? It's the first line of defense. This is really why it matters. We're getting all of that trash out there to protect the equipment that is downstream and the treatment processes that are downstream. That in turn reduces wear and tear, emergency downtime, and the maintenance costs associated with the equipment that you have downstream. Sets everything up for success. And of course, all of this really directly supports the regulatory compliance under your NPDES or state discharge permits. Some systems, depending on whether they're discharging, doing land application or discharging into water of the United States, will have one or the other. There are some systems that have both. When headworks fail, in other words, when they're not maintained or when they break down and aren't working correctly, a lot of bad things can happen. Pump ragging is a common one where essentially rags, wipes, things that don't belong in the influent stream jam up pumps and either damage them or break them or the motors that are running them. This can cause lots of expense, significant downtime, and if you don't have redundancy built into your plant, this can be really a problem. Grit accumulation, that sand and gravel that we were talking about, if it's not removed appropriately over time, it will accumulate in other parts of your treatment train, particularly in your primary treatment, which is the next stage after the headworks. So you can end up with grit in your basins. And this will over time reduce treatment capacity because there just won't be as much room in the plants or in those basins for the various processes to do what they need to do. And of course, wastewater is not clear, so if you're not paying attention, you won't see it until it becomes a problem. The grit also, again, damages pumps, variety of rotating equipment that you might have downstream, and there's typically a lot of that in clarifiers and scrapers and things like that. You also have the ability to really upset your processes if you are not paying attention to what's going on in your headworks, just like a major plug in the collection system can cause wastewater to become septic and therefore deliver a shock load to your treatment plant when it eventually gets there. As we'll see, the first stage of screening, which is bar racks or trash racks, they work as sieves if they're maintained, and if they're not, they turn into a dam, which then leads to backup, which can lead to septic influent hitting your wastewater system. All of those things, at least if they're not handled correctly, increase your compliance risk, increase the possibility that you're going to have permit violations, that you're going to come under further regulatory scrutiny, and in some cases, particularly if you have, for example, an overflow outside of your treatment facility because of this, come with potential fines. And of course, as I mentioned, and as I will mention repeatedly, reactive repairs, emergency repairs are way more expensive than doing proactive maintenance. So this is, again, one of those areas where you really want to pay attention to what's going on and follow your SOPs. There's also, of course, the regulatory context that we have to think of, which I've kind of alluded to. Clean Water Act is what's sort of established all of our federal framework for wastewater treatment standards. Note that in some cases your state treatment standards might be actually a little more stringent. Every NPDES permit has facility-specific effluent limits and may have facility-specific treatment requirements. If you are working at a utility in any context that deals with the operations or decision-making, it is a really good idea to read and understand your permit so you know what you are liable for. State discharge permits had similar setups, similar effluent limits and requirements for solids handling, et cetera. You might even have specifics, components of Headworks required as part of facility design standards. I can't obviously list them all because we've got multiple jurisdictions here. This is one of those, areas where you really need to understand the regulatory framework in your state because that's what's going to apply to you. So requirements vary. It's really important to know yours. Let's talk a little bit about core components, which are fairly basic. Again, most of them are related to removing trash. We're going to talk about screening, grit removal, flow measurement, equalization, and then odor control, which is often a part of that. Step one is screening. We're basically removing the big trash, wood, debris, plastic wipes, large solids that are in raw wastewater. Again, this is entirely designed to protect the downstream processes and protect equipment. It's a pretty much completely physical process. And you may have, as we will see, layers of screens designed to capture different size detritus that is coming in your effluent stream. Manual bar racks look something like this. They're typically slanted racks that sit in the effluent stream and physically just trap debris. They obviously have to be cleaned, or as you will see there, things will back up over time. There are manually cleaned racks that are typically going to be in smaller plants or in bypass channels at larger plants. The other option is that you're going to have a mechanically cleaned rack system. These could have rakes in the front, they could have them in the back. There are pluses and minuses to either setup. They're usually either timed or driven by pressure differentials so that you don't have a lot of head loss associated with them. But even the mechanical ones need to be maintained. There are motor, there are pumps, there are gears, there are chains, there's lubrication needs, and they can be somewhat dangerous to be around. So these have to be maintained very, very well. This stuff is typically made of aluminum or stainless steel. Obviously, it's in water all the time. We can't have corrosive metals in there. How they are described varies a little bit depending on the size of the rack we're talking about, but also to some degree on where you are in the United States. There are different vernaculars that are used, but sort of typically if it's 3/8 inches to about 2 inches, it's called a bar screen. Anything that's 2 inches or bigger is usually called a trash rack or a bar rack. And again, they can be manually cleaned or mechanically cleaned. This is a very typical sort of small system setup. You can see some trash on there, slanted. There's a walkway above where the technicians can use just big rakes to pull trash up. Wanted to point out that just below the feet there, you can see that there is a trough. That's where the trash goes so that it can be dewatered. You can't just pull it out and throw it away. You have to get rid of the liquid that is associated with those screenings, and that will, as you will see, work its way back into the effluent stream. Mechanically screened screens, this has got a little short video here that kind of shows how they might work. This one happens to have the cleaning rack on the front. Some come on the back. If they're in the back, they jam less, but they don't clean as well. The front one clean versions tend to remove more trash, but they're a little bit more liable to jam. But basically, what we've got going on here is a set of teeth on a rack that are controlled by some pressure switches upstream and downstream that let it know basically when enough trash is built up that it needs to be removed. It's pulled out, it's dewatered along the way, and then fed into some sort of disposal system, usually a hopper. There may be long channels depending on the size of your system, or conveyor belts that move it. Which leaves us with a bunch of screenings that we have to do something with, right? The trash has to go somewhere. And there are some very critical steps when dealing with screenings. Number one, as I mentioned, they have to be drained back into the influent. Typically, they're wet. There's a lot of organic matter still on them, which can include disease-causing organisms. So at a bare minimum, they're going to have to be drained before they're dealt with. We'll talk about disposal a little bit more in a bit, but one of the key things to remember about screenings and grit is that you don't want them laying around the plant for a long time because they can attract flies, they can attract vermin, they can cause odor complaints. And as you can see in the bottom right-hand corner, somebody hasn't been doing a great job in this particular instance of making sure that all of the screenings end up in the hopper that they're supposed to. I've got a slide in here about some basic design considerations. I'm not going to go over this, but for those of you who want to read the slides, just gives you sort of a breakdown of which kind of screens typically are used for what size trash. So we get all the big stuff out, but obviously there's some gaps in those bars and some trash is going to make it through. So the question becomes, what do we do with that? The next step is either finer screens or a combination of what we call coarse solids reduction and finer screens. So in this case, basically what we're talking about is industrial sized versions of the garbage disposal you have in your kitchen. They're not designed to remove anything. They're designed to chop it up into a manageable size that will facilitate flow through to the next stages, essentially preparing debris for ladle removal, not removing it at this stage. And for doing this for the exact same reason that we get the trash out, it's all about protecting downstream processes and equipment. There's three main types of coarse solids reduction equipment that you're going to see: communitors, grinders, and macerators. Communitors are kind of the older version, typically aren't installed these days, but you see them in a lot of older plants. Communitors and grinders essentially do the same thing. They're sometimes called sewage grinders. There's definitely sort of a line, blurry line in between the two of them. But all they're going to basically do is shred anything that comes in, which will include, hands and feet if you get them stuck in there. They're typically found in older plants. And nowadays, in most designs, grinders tend to be installed upstream of the plant, although there may be some in the plant as well. So we'll often see these in lift stations or further up to protect pumps at lift stations and things like that. The pros of these is they can take care of the place of some of the bar screens, and of course overcome the disposal issues you have with the bar screen components themselves. But again, what they're doing is chopping bits up. You still have to remove it later. And of course, whereas like a manual bar rack is essentially just run on people power, you need electricity to run a commutator. You still have to remove the shredded debris. They can be labor intensive to maintain. You're gonna need some sort of redundancy or bypass channel if one of these does get clogged, or if you've got high flow issues that you need to deal with. Grinders look very similar. There are a lot of different sizes for a lot of different applications. They essentially do the same thing, although again, these days grinders tend to be installed somewhat upstream in lift stations and things like that. So this is an example of a grinder in a flow channel at a pump station. So you can see this is the upstream version. So debris is going to get trapped in that semicircular basin there, and those grinders just spin around and turn everything that's in there into mincemeat. And then this is the downside. Oops, excuse me, one too far. This is the downstream side, as you can see. So it's basically the goal here is chop any debris small enough so that it can make it through those holes. And if it can make it through those holes, chances are it's not going to damage equipment further down. And we will theoretically have equipment further down the line that will help us remove it. The last version that you're going to sometimes see are what are called macerators. These are typically in-pipe installations. They work better with small solids like wet wipes, plastic bits, and hair. And they're kind of like a little wearing blender. You can see in the image on the right there, the flow comes in from the left-hand side. That blade will spin around. There's a trap at the bottom for any rocks or bigger pieces that have made it through to protect the equipment. And what ends up going out the other end is very, very fine, chopped up matter that still needs to be dealt with, which brings us to our next topic, which is the fine screening stage. So the bar racks are taking out the big stuff. Fine screens are going to take out whatever is left and whatever's been chopped up by our coarser grinders there. Again, the goal here is exactly the same as the goal of the earlier stages, protecting the downstream equipment and protecting the downstream processes, but we're basically just trying to remove those fine screenings. There's a lot of different types, different technologies that get used here. Steps, perforated plates, wedge wires, static screens, rotary drums, and probably some others that I don't have listed. What you're looking at right here is a step screen, which I sort of think of as analogous to an escalator, right? Influent is coming in from the bottom with all of this chopped up mess. You can see the teeth are grabbing all the particulate matter, pulling it to the top where it's being dropped into a trough and then sent along its merry way. This is the sort of the bigger picture, and you can see there's drains. Works more or less like an escalator. This one has sort of wire screens in it. There are similar versions that use perforated plates. So this happens to be one down in Gatesville, Texas, system that we've worked with on multiple occasions. And you can see it's basically the same sort of escalator type situation. Those plates have holes in them. Anything smaller than the hole goes through, including the liquid. Bigger pieces stay trapped. And you can see about every fifth or sixth belt, there's some teeth that is going to grab larger pieces. The influent is coming in at the bottom of the screen. It's being dewatered as it moves to the top. And then once it gets to the top, it goes through a hopper after being dewatered a little bit more. And you notice there that that hopper is not all that large, because again, this is one of those things where you want to get this stuff out and you want to get rid of it in a reasonable time. You don't want this stuff sitting around attracting vermin, causing smells, and potentially getting people sick. Up close, the perforated plates look like this, very simple, just like a sieve. Anything smaller than the holes goes through, anything bigger than the holes stays in the equipment and is disposed of later. Another option you might see is wedge wires. This happens to be set up from a small plant in Tenino, Washington. They have two of these setups, and it's a very similar situation. You've got these wires with teeth that push up through them. They're grabbing materials at the bottom, pulling them up this process, and then the detritus sort of falls off the end and gets dealt with. They've got two of these. They can handle about 750,000 gallons per day each. But one thing to be really aware of, particularly as you are trying to solve Headworks related problems, is to make sure that your processes are compatible. The operator that runs this particular facility mentioned that they have recently installed grinder pumps at the lift stations in their collection system. And one of the byproducts of that was that the grinders were actually creating particles that were too small for this wedge wire setup to actually effectively remove. So by fixing one problem, they actually created another. So this is, again, a design consideration, planning consideration, particularly when you retrofit. When you're grinding, you got to make sure that the equipment that you have downstream that is going to be removing those particles is capable of removing the output of your grinders. There are also static versions of these, static screen, which essentially has few to no moving parts. You can see one in place on the left and a cross section on the right. Essentially, we've got the influent coming in. There's an aeration process in the basin, sort of at the top, that yellow bit. The aerated water goes over the top along with the detritus. The water falls through the screen, which is perforated and moves on to the next stage of treatment. The solids slide down that parabola parabolic screen, end up in a worm screw, which dewaters and moves them on to the next stage for treatment. These are very quiet. They pretty much only need regular cleaning. The screen itself doesn't really have any moving parts, although you, of course, need pumps to run the aerators. You need motors to run the worm screws. And you've got sprayers. They do require some maintenance because there are going to be organics that build up and biofilms that build up if you don't maintain them. The last version I'm going to talk about are rotary drums. Again, these are all versions of the same thing. There's some sort of perforated mechanism that allows liquid to flow through and solids to be captured. This one happens to also be at Gatesville. So you can see they've got multiple stages in place handling different sized detritus that is in their influent stream. These basically work by pumping the influent into the middle. The drum is spinning around. Centripetal force is forcing the water out, and then at the bottom, the solids discharge onto their next stage, and they're both dealt with. Got another table for you that we're not going to go over, but it just sort of gives you an idea of the kinds or the sizes of screenings that these different kinds of mechanisms can handle. And notice that, for example, rotary drums show up there twice because depending on how they're built, they may be designed to deal with different sized screenings. So you might actually have a series of rotary drums looking at finer and finer materials. As I mentioned, once you've got the screenings, you've got to handle them, and it can be pretty substantial. You know, 1 million gallons of water could generate anywhere from 1.5 to 8 cubic feet of screenings. So if you've got a large plant, you're probably gonna have a large amount of material you have to deal with. And obviously the smaller the openings in your screens, the more stuff you're going to catch. Those screenings, as I said, have to be dewatered because there's gonna be some organic matter included on them, and they have to be disposed of. How they are disposed of is gonna kind of depend on the specific situation. Some places they're incinerated, and some places they go to landfill. Again, this is one of those know your local listings or check your local listings kind of situations, because the requirements may vary depending on where you are, what your screenings consist of, and there are typically permit requirements around these. But as a general rule, you don't want this stuff to build up. A small plant might not collect a lot a day, but you do want to have a very robust screenings management plan so that they're not sort of building up, for example, over the winter and then sort of sitting out there and rotting when summertime comes. So that's all the big trash. What's left in the stream? Well, a lot of organics, which are suspended, hopefully, and a lot of grit, typically, which are things like sand, cinders, rocks, coffee grounds, eggshells, seeds. It's mostly inorganic material that isn't digestible, but can also include some organic material that, although theoretically digestible, is not going to be dealt with in the detention times for the processes that you have in your system. So like, you know, an eggshell will probably break down over time, but not in your wastewater treatment plant. This is the abrasive stuff that I was talking about that typically is gonna accelerate wear on impellers and pipe interiors and rotating equipment. The larger trash is gonna jam things up and block things. The smaller stuff is typically gonna wear away at equipment and also has the potential to settle and accumulate in tanks, which is going to essentially steal capacity from your aeration basins. And over time, if that accumulation gets big enough, your calculations are going to be off because the volume of your tanks are not going to be what you think they are. This stuff also doesn't degrade. Once it's in your system, the only way to get it out is essentially shut down the basin, clean it out, or get some sort of a pumper in there. You're going to have to do maintenance to remove it, and that can be costly. It can be disruptive. So grit removal is a really, really important stage to protect that equipment and to protect those processes. Typically, we're talking about small particles, so like, you know, 1/5 of a millimeter, and things that have a specific gravity about 2.5, which basically means they're 2.5 times as dense as water, which is an important thing to remember because using that information is how we remove grit. We do that by basically slowing the velocity of the water that it's in, so slowing the flow down to around 1 foot per second. And at that speed, assuming we've got a grit channel or a basin that's designed to handle it, what will happen is the grit will settle out into the bottom of the channel, while the organics that we're going to deal with in primary sedimentation and in biological treatment phases will stay in the water. So this is basically a way of sieving out or letting the grit and stones sort of fall out of the flow simply by controlling the velocity of the water. This is a top-down view of what a typical sort of basic grit channel looks like. Usually you've got at least 2 channels so that you've got some redundancy for repairs, maintenance, and flow stabilization. They're narrower at the bottom than they are at the top. They're typically, the length of them is typically pretty long. They might be 50 feet or more, but it's designed with that sort of 1 foot velocity in mind, so that the vast majority of the grit that's in the effluent at this stage falls out in the channel and doesn't get through. And you'll notice that there, the top there, we've got influent going back to the plant. We have a dewatering drain, and then of course, in some very basic versions, you might actually have to drain one side and manually remove grit, but usually there are mechanical scrapers that are working on the bottom that are slowly taking the grit out of the channels. Got another table for you. Again, not going to read it, but this is just sort of a description of what the individual pieces do. If you want a more in-depth view of these specific processes, we have another webinar series that we did recently that was designed for operators that are trying to pass their certifications, that go into the real nitty-gritty of these. But most of these are going to have similar components where you've got, settling areas and weirs and dewatering drains and things like this. Real basic setup might look something like this. This one happens to be in Kenya. This is not currently in service and arguably is an example of how not to do it. You'll notice that there are piles of grit on either side that they've pulled out of the channel. That is not a good practice, but this sort of shows you the order of operations, where you've got your bar racks, in this case manually cleaned at the front, and then you've got these grit channels immediately behind it, and then you've got your next stage processes off to the right here. Just in case you weren't sure, that's the grit channel right there. So they can be really, really small if you've got small or low flows. They can be huge. You can also end up removing quite a lot of grit, usually less than trash, but it's anywhere from 1 to 4 cubic feet of grit might be removed from every 1,000,000 gallons of water. This is the sort of basic non-aerated version. There are aerated versions of grit removal processes as well. But basically, all of these processes work through what's called sedimentation. The idea is that the grit is denser than water, so given enough time, it will sink to the bottom. We've got a flow velocity through the channel, so it's moving, in this case, left to right at a specific velocity. And if we give it enough time, the particle will fall to the bottom of the tank. And there's some very basic math that I'm not going to go over, because again, that's not what this session is designed for. But we can use that basic math to both adjust the flow rates in our system, and also to verify that the flows rates that we have are appropriate for the facilities that we have. There are other options for grit removal, which basically use, in one case, very similar principles, and in another case, very different. We have aerated grit chambers, then we have what are called cyclone and vortex separators. And an aerated grit chamber is basically a high-tech version of a grit channel, where we include aeration into the system, because aeration, that air-water mix is even less dense than water, so the grit tends to fall faster. These typically have automatic grit pumps. The aeration also induces some currents into the flow, which helps push the grit to the bottom. So the idea is we've got, this is a cross section, we've got some air being dispersed into there, which slows the velocity, and then also lowers the specific gravity of the water, so that the relative specific gravity of the grit and the fluid it's in are even broader. That rolling action by itself induces some currents. Those currents, again, help facilitate moving grit down toward the bottom, where it sort of moves into a channel that has mechanical scrapers. Detention time on this kind of setup is typically pretty low. So, the flow in there, any sort of given section of water is going to be in there for about 3 to 5 minutes. These are very efficient, but do need some space. Other options are cyclone separators, which work more or less like the dust collection systems in a woodworking shop. If you've ever been to one of those, basically the influent comes into the chamber at a tangent. That by itself creates a vortex. The grit falls to the bottom, water leaves near the top. One of the benefits of these is they don't have any moving parts, and they are relatively compact. So they've got a relatively small footprint. It's the influence stream, again, that creates that cyclone. Of course, you're going to need an auger mechanism at the bottom to move the grit that you accumulate out. And of course, you're going to need some pumps probably to regulate the flow. So there are still energy needs. You still need core screens upstream, but this is another way to address grit without using a channel. So it's an approach that uses typically a smaller footprint. That being said, the flow and the pressure have to be monitored fairly well, because these will only operate correctly within a range. And although this picture is showing it sort of vertically, typically they're set at an angle, something like this. And here you can see sort of the auger mechanism in place. Last but not least, for today, we've got vortex separators, which are just fancy versions of the cyclones. They're typically proprietary. They are typically pretty efficient and designed for very, very small particulate grit. Again, pros, no moving parts other than the pumps you're using to generate them and the sumps to pull the grit out. They provide pretty consistent removal efficiency over wide flow ranges, and they have a very small footprint, but you're going to need redundancy. And because of the way they're designed with the grit sump being at the bottom, if you get clogs down there, they can be a little bit more difficult to repair than some of the open channel type situations. So a lot of different ways to get grit out of the system, but like the trash that you remove, you've got to do something with it. And what you do with it is going to kind of depend on what shape that grit is in, or what the quality of the grit is in that you take out. If for whatever reason your grit ends up having a high amount of organics on it, as I said, we don't want any of this stuff soaking wet when we try to dispose of it, but we also want to get rid of most of the organic matter to avoid those nuisance smell and vermin problems. We might have to wash the grit. So you might have a grit washing setup that typically looks something like this. It's essentially a large washing machine, essentially, where the grit flow is pushed in. Now, this is the separated grit from prior steps is put in. It's agitated inside this basin. There's a weir at the top so that the water flows out, or the effluent flows out the top, and then the now cleaner grit moves up a worm screw or along a belt out to a discharge bin where it is sent out. So got another poll question for you just to see kind of what's in use out there. What kind of grit removal process does the system that you work at use? And you may have more than one, so feel free to check all that apply. So are you using grit channels, aerated grit chambers, cyclones, vortexes, and are you using a grit classifier washer, which is what that last piece was that I showed you?
I'll give people just a couple more seconds to get their answers in. All right, it looks like most folks have answered now. 15% say grit channels, 9% say aerated grit chamber, 10% say cyclone or vortex separator, 5% say grit classifier, and 72% say don't know or not applicable.
All right. So a lot of technologies out there, a lot of them being used as we can see, and there's always new things being developed. So, as your plant grows and your needs change, it's a really good idea to sort of keep on top of what's available, but not necessarily go for sort of the fanciest thing with the most bells and whistles, because every one of these pieces of equipment has to be maintained, and there are maintenance considerations with all of them. So what you want to make sure you're doing is using something that's appropriate for the size of your facility, appropriate for the kind of grit that you're dealing with, and appropriate for the kind of maintenance that you can do or are willing to do or can afford to do. All right, so let's move on to our last steps, which revolve around flow measurement. And this is one of those things that you should do and you typically also have to do. NPDES and state discharge permits typically require accurate flow reporting. It's a direct regulatory requirement at virtually every facility. So this is something to pay attention to. Because you have to do it, and it's the only, or one of the only ways that you can prove that you are staying within your permit limits. And as I mentioned, there are a lot of smaller systems that I've dealt with where this is sort of the piece that breaks down first, whether it's due to equipment failure or calibration drift or what have you, or just lack of maintenance on sensors. This is really, really important. Most permits give the regulator the ability to show up and check your records, and you want to make sure that you've got contemporaneous records, and you want to make sure that they're accurate from a permit standpoint. But you also really need to know what your flows are so that you can actively manage the processes that you have. It's important for process control. So whether you're talking about chemical dosing or flocculant dosing or hydraulic loading decisions, detention time, recycle flow management, all of this depends on knowing the flow through various parts of your system. So typically you're going to have flow measurement at multiple stages, but this first number is really important. It's also really important for things like capacity planning and operational insight. If your system develops an I&I, so infiltration and problem, an inundation problem over time in your collection system, one of the ways you might notice that is a change in flow patterns related to wet weather events, right? If suddenly a bunch of manholes are open, or a piece of your collection system is now suddenly in an area where it's constantly inundated during wet weather, knowing what happens at the front end of your system, being able to correlate changes in flow with changes in weather can give you insight to what's going on in your collection system. It can give you information about changes in diurnal patterns. We saw that during the COVID era when a lot more people were staying home, and in some places, flow patterns at the wastewater treatment plant actually changed a little bit and had to be accounted for. It's also really important for capital planning, capacity planning. Most communities don't stay static. They either grow or they shrink, and sometimes they do both of those at different times, which can lead to two problems. A plant that's under capacity, in other words, you've got a community that's growing faster than the plant was designed for, or you might have a situation where people are moving away from the community and suddenly the plant doesn't really have the flows it really needs or that it was designed for. So again, if you are measuring flow, if you're recording this kind of information, it can give you insight that can be used in a lot of different ways. Flow is going to be measured a lot of different ways. There are a lot of different tools. The goal here is not to sort of exhaustively go through which might be best for your current situation. My main point is that the flow should be measured, and you should have something that is appropriate for your system. And to think about, if you've got failing equipment, think about what might be appropriate and what's gonna help you in the future. So you might have, weirs or partial flumes or ultrasonic meters or magnetic flow meters. They're all very accurate. Some of them are simpler to maintain. Some of them are slightly more accurate. But the point is, you really want to be able to measure those flows for the reasons that I talked about. Last but not least, we're going to talk about flow equalization and odor control. Again, this isn't used as much here, but as we noted from our earlier poll, there are some systems here that use it. And basically, this is just to help you even out the flow patterns. It's also a strategy that can be used to facilitate a longer life of a plant that maybe has outgrown its capacity, at least as initially designed. Typically, plants aren't running full bore all the time. You've got those high flows resulting sort of from morning activities, and then it tapers off and then picks up again in the evening. And one way to deal with increased growth is to add flow equalization tanks that allow you to essentially capture and hold some of that flow so that you can have a more even flow through your system. Obviously, they have to be sized to account for extreme flows, particularly if you've got a combined system like I was talking about. And if you have this, or if you were thinking about this, aeration is pretty much mandatory, because depending on how long that sewage sits around, if it's not being aerated and agitated, it's going to go septic, which leads to those shock problems we talked about earlier. Aeration tanks can be huge. This is an older picture from the 60s, but you can see these are some very, very big tanks associated with a specific plant. I think this one is actually in Germany. Side part of this is odor control. Obviously, maintaining your headworks efficiently and getting rid of the trash and grit that builds up is step one. There are other odor issues that can happen further on in the processes, but smells at wastewater plants are typically the result of organic decomposition. There are a lot of compounds that can cause smells: hydrogen sulfide, ammonium mercaptans, indole, scatol, things that are either generated by the decomposition or that are just part of the wastewater itself. Scatol and indole are part of feces, part of why it smells. Aeration, capture and treat, removing screenings frequently. These are all management strategies that you can implement if odors are an issue. And I do want to point out that there are a lot of other gas byproducts, some of which are not necessarily good for us, like methane, that are part of wastewater treatment that don't have any sort of smell, but can be problematic as well. Gas control, odor control, something to pay attention to, which brings us to O&M considerations. All of this stuff has to be maintained. Every wastewater system, every collection system should have an up-to-date operations and maintenance manual and SOPs and training, so standard operating procedures and training, particularly safety training, that goes along with them. I know a lot of plants that operate entirely without them. And in theory, if you're an experienced operator, you might think that's okay, but you're going to leave eventually. Somebody else is going to come in. So it's really important to have those processes written down so that we're just not winging it, and then also so that we can monitor and log what things are going on so that we can deal with them. Daily inspections of headworks are, in my opinion, mandatory. Making sure that the screening operations are working correctly. Like I said, those bar screens, if you are not paying attention to them, the sieve turns into a dam. Same thing with the grit system. Is grit making it past the collection systems into other processes? Are there odors that aren't supposed to be there? Are your screenings containers filling at the rates that you expect? Are you disposing of them appropriately on an appropriate schedule? Are your flow meters doing what you expect? You spend some time working in a wastewater treatment plant, you get to know or get very familiar with sort of daily flows, seasonal flows, and the changes that are resulting of them. And even flow meters have to be maintained. They have to be installed correctly, but they do have to periodically, typically have to be calibrated. Sensors, particularly in flumes and weirs, might need to be cleaned on a regular basis to make sure that you're getting good readings. And if you've got a SCADA system or if there's an electronic transmission of data from those sensors, that has to be maintained as well, because signals can get dropped. So it's really important to sort of keep on top of those, take those readings on a regular basis, because when things go off, that's a signal that something isn't going right. And then, of course, safety is paramount. Make sure that the appropriate PPE is in use, that staff are trained in emergency procedures. If you've got enclosed spaces, that you've got monitors, that people aren't going into enclosed spaces that might have hydrogen sulfide or other gases built up in them without the appropriate training and equipment, and making sure that confined space and emergency equipment is going to be available and accessible, and that people know how to use them. Common failings we see at the Headworks, things like screen blockages, downstream ragging, grit carryover, basically all of the things I talked about at the beginning that are likely to happen if the screen isn't maintained. And we've got sort of some basics. This is not an exhaustive list by any stretch of the imagination, but these are some things to sort of pay attention to and some root causes that you might be running into. Weather and seasonal operational changes are also something that you really need to be aware of for the reasons that I talked about before. Again, if you've got significant I&I problems, those are going to impact your plant. You really need to be aware of them and prep for them, or be at least logging information so that you will notice over time when those problems develop. Obviously in cold weather, we've got basins, there's a lot of water around. You want to make sure that people don't slip and fall. Freeze protection might be required in some parts of the country. There are wastewater treatment plants in Alaska that are entirely enclosed because of the temperature issues. And every spring, it's a really good idea to sort of inspect your equipment. Again, if you've got a good ops O&M plan, that will include information on when specific equipment needs to be checked, maintained, lubricated, etc., so that you can stay on top and, again, stay more proactive than reactive. There's always going to be some reactive maintenance that's required, but you want to be on the proactive side of things. Ancillary to that is, redundancy in your system and having spare parts. And again, where you are located in the United States is going to impact decisions about this. If you're in a major metropolitan area, things like screen rakes and teeth and drive chains and grid impellers might be readily accessible and deliverable within a couple of days. If you're out in the territories, for example, in Guam or CNMI, everything has to be flown or shipped in. So we're not talking about time frames of a day or two, we're talking about months. So you have to plan accordingly. You need to be aware of what is going on in your system, what things are likely to fail, what you need to have on hand, what you can get quickly, and pay attention to pricing if you can as well, because particularly right now, things are changing pretty quickly. Also, making sure that the redundancy that's built into your system stays in your system. So, most facilities will have 2 screen channels. Most lift stations have 2 pumps. Working with a system here recently that had a lift station where we found out that one of the lift station pumps had been out for a really, really long time. Nobody really knew it. And the other one wasn't working at full capacity either. And when we did the math, we realized if that second pump went out, they only had about 14 hours of capacity before that lift station overflowed. So you need to be aware of what's going on throughout your entire system, but again, at the Headworks as well, because problems there can sort of run through the entire plant. Safety is obviously paramount. I've kind of touched on this, but there are a lot of hazards in wastewater treatment in particular, and can be around some of the equipment we have at Headworks as well. So there's mechanical hazards, there's gas hazards, there's electrical hazards. If you're having to do confined space entry, you want to make sure that that's done appropriately and permitted correctly. Water safety is huge. Particularly aerated basins don't provide any buoyancy, and if you fall in, there's zero visibility. So you want to make sure that everybody knows what they're doing, that the appropriate safety equipment is available, like flotation devices and things like that. So as you've probably gathered, I kind of repeat this, the Headworks performance is going to impact everything else down the system, whether it's influent pumps going down, digesters, dewatering equipment, whatever. And although most of the systems are fairly basic and don't need a ton of maintenance necessarily, it is really important to recognize that, as I said, proactive approach to maintenance is better than a reactive one. Pump repair could cost $5,000 to $25,000 depending on the size of the pump. Cleaning out a grit basin can cause significant downtime and expense. All of these things can turn into unplanned events, which are always more expensive. Running a little short on time here, but I just want to point out a few things. related to capital planning, some strategic decisions that you have to think about. Everything in your plant, in your collection system is going to deteriorate. Screens might last 10 to 15 years. Grit removal systems, depending on what they are, might be 20 to 45, could be less, depending on how they're maintained. Asset management is a really good way to stay on top of this, but even a simple spreadsheet where you're basically tracking equipment age, condition, and maintenance history is going to give you a much better way of planning for the future, so that you are seeing things deteriorating and intervening before they fail. Some things might be okay to run to failure, but other components of a wastewater treatment system plant are not ones that you want to let run to failure. And although there is a lot of money available for public wastewater treatment plants for improvements through state revolving funds, U.S. rural development, individual state-specific programs, in order to qualify for these, you have to be prepared. You have to have shovel-worthy and shovel-ready projects. And although TA providers and your regulators can help with these process, it's really important to be ahead of the game and to know what you're going to need and when you're going to need them, because the timeline for project funding, development, planning, construction, it's not short. Even relatively simple projects can take 3, 4, 5 or more years from inception to completion. So this is really one of those early bird gets the worm kind of situations, or at least an early bird has a better chance of getting the worm. If you wait until equipment is broken or obsolete or failing to start planning, you're going to be too late. Again, these processes are measured in years, not months typically, unless you can write the check yourself. And even then, because of the permitting and the planning, it takes a long time. So very broad overview, I realize that. Key takeaways: Headworks is the foundation of your treatment system. What happens there affects everything downstream. We've got some very basic critical components: screening, grit removal, flow measurement. This is all mostly about removing trash so that the processes downstream work the way they're supposed to, and measuring the flow and adjusting the flow so that you can keep your processes in balance. Try to be proactive if you can. It's always cheaper to do that way, and collect and monitor Headworks data, because it's going to really tell you a story about your collection system, so upstream, and your facility health. And last but not least, of course, there's a lot of money available to make upgrades, but the timeline for getting that and for getting those projects implemented is quite long. So start early. So I realize we're a couple minutes over time. I'm happy to stick around and answer questions. I apologize for the extra time, but if there are any questions, Zoe, you want to fire off, I will do my best to answer them. And if for some reason we don't get to your question, or I don't have an answer for you now, there's my contact information. Feel free to reach out to me, or the EFC or the EFC network. All of us are happy, ready, willing, and able to help you.
All right, we'll try to squeeze in just a couple questions, maybe wrap up at 2:05. But our first question is, how important is back power generation in the Headworks phase of wastewater?
So I'm not entirely sure what you mean by that. Part of the Headworks sort of detritus elimination process can be incineration. If that's what you're talking about, some facilities are going to actually generate power in other stages, whether it's through digesters or through incinerators, to power some of that equipment. But I'm not entirely sure what you mean by that. But Zoe, I'm assuming that we have the identity of the question asker, so that's something I'm going to have to get back to you on.
Yeah, he meant backup generator. Sorry about that.
Oh, back up. Oh, yeah. Backup generators, very important. And if you have backup generators, those have to be maintained as well. We had an incident out in the territories where a typhoon came through, and the generators had to be fired up because the power went down, and because the generators hadn't been maintained, and in some cases it was something as simple as not having diesel in the tanks, none of that worked, and they had subsequent overflows at lift stations and things like that. So if you have powered facilities, having a backup power generator is pretty critical, unless, of course, your system is designed for manual bypasses. So, for example, if you've got mechanically clean screens and the power goes down, you might be able to run that through a manual bypass channel and deal with the screenings that way. But and this is, again, one of those things where monitoring activities and monitoring your system is important, because that will give you some idea about how much time you have to react to something like a complete power failure, right? Like I said, those bar screens are going to turn into a dam eventually. That may take hours, that might take days. It's all going to kind of depend on your specific situation. But if you've got critical mechanical processes anywhere in your system, it's really good to have some backup power to run them. And again, to test and maintain that equipment and make sure that it's sized appropriately for your system. And this is a thing to check with your individual state regulators for. For example, I know here in New Mexico, there was a program going around a little while ago where some of the counties were specifically, as part of emergency response plans, looking to help utilities or groups of utilities finance backup generators. So that was a specific funding program for that specific requirement, because many of these smaller systems just didn't have that. So hopefully I've answered the question.
Yes, thank you. And there's a couple more questions that I'll send to you after this webinar, but it looks like we have met time. So huge thank you to James for sharing his expertise with us today. Following this webinar, you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following the webinar, so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics important to you. Thank you again, and we hope to see you at future EFCN events. Have a great day, everyone.
Thanks for joining.